All right, we'll continue our discussion. Just one small correction. This is 3-1. Okay, this is triple zero. Triple zero. Nothing changes, but just correction. So we have been seeing how the process that generates the data helps to find the future outcomes is called probability, and the data which is generated helps to infer the process is called as inferential statistics. Okay, this is a cycle. So I safely assume that the probability of x is 1 by 2. Okay, because it's known. But how do we know? Okay, suppose if we toss a coin, okay, and if you really want to find out what is the probability of getting heads, okay, how do we know? Okay, so the process of trying to find out the probabilities or estimate the probabilities from the data is what we call it as maximum likelihood estimate. Okay, in real world, okay, in most of the problems in real world, we will only have the data and we will want to estimate the probabilities from the data. Okay, nobody comes and tells you that the probability of heads is 0.5. Nobody tells us, because in high school all the problems they will have the probabilities given and we wanted to find out something. So life becomes easy. Okay, but the challenge when it comes to real world is we don't know these probabilities and we'll have to estimate from data. And that is where the real challenge is. Okay, that is where the machine learning, data science, statistics, everything helps us to find the probabilities from the data using methods. Okay, and maximum likelihood estimate is trying to find out the probabilities of an event from the data. So we always use the term likelihood, okay, along with probability, but both are not the same. Okay, probability is the chance of getting the next outcome. That is probability. Likelihood is the reverse. Likelihood comes from the data. Okay, and MLE is a process by which we use to estimate it. Okay, let's take the same example of coin toss. Okay, and 10 is a very small experiment. Let's make it 100. Okay, I toss the coin 100 times. Okay, and I don't know what is the probability of heads. Okay, I don't know. It's we assume that it is 0.5 because we have been using it for since ages. But assume that for our coin, which we tossed 100 times, we wanted to find the probability of our heads. Okay, now this is where we wanted to start making assumptions about the probability distributions. So when we wanted to find something from the data, we make some assumption about the process which generated the data, because without assumptions it's very difficult, because you could have a coin which may be three-sided. Okay, we don't know how the coin is, but it could be three-sided. Okay, I mean, it could be like a triangle and we don't know heads, tails and something in between. Okay, so we assume that okay, I mean, the question now is not to find whether the coin is fair or not. If the coin is fair or not, we use hypothesis testing, and we then use the p-values to determine whether this coin is fair or not. Okay, and as I just recap, the p-value is helps us to quantify the rare event. When the surprise is more, but still it has happened, then you kind of scratch your head saying that I didn't expect this to happen, but data shows that it has happened, so probably the coin is not fair. That's the reason when there's something which is status quo happens, it is we accept the null hypothesis. Okay, and we just assume the null hypothesis is true. But in order to prove that the null hypothesis is not correct, we need more evidence, and that means that the event is rare. If I wanted to prove that a person, a person has committed a crime, okay, I just cannot go and assume that he has committed a crime. I want more and more data to prove it, and the probability of such thing happening is normally rare. Okay, nobody makes crimes. Okay, only extreme cases people do make crime, and in order to find out the extreme cases, we need to find evidence, and the probability of that, if it is so low, but still it has happened, the data shows that it has happened, then we claim that okay, probably the person is not innocent. The data shows that the rare event has occurred with low probabilities, very low probabilities, but we accept that okay, you might be guilty. Okay, that's the reason we need the probabilities to be so low to accept something. That's the reason the alpha values are like 0.05. Anything which is below that, okay, points out of like 0 to 1, 0.05 is very towards the end of this, right? And we have 95% of the data where it says that the person would be innocent. In order to prove that he is guilty, the probability should be like the data should fall into a bucket which is like very low, okay, in the 0 to 1 scale. Okay, that's the reason we use this. And if you wanted to be very stringent in 0 to 1 scale, if you keep it like 0.0, 0.1, which means that you have 99% of the chance that okay, you can prove that he is not guilty. And if the data shows that the probability of that event occurring falls here, such a rare event, such a surprising thing has happened that even though I tried to prove that he is innocent, I mean, I believe that he is innocent, the data shows that the person has committed crime, such a crime that it falls into this bucket of 0.1%. So this is the alpha values, 0.05 or 0.1. So I am accepting that, or I'm failing to reject I'm rejecting the null hypothesis and accepting that he has made a crime. Okay, that's the idea. Okay, so sorry, I just took a detour. I'll come back here because it's very important to understand the difference between likelihood, probabilities, and the process which generates it. Okay, and I was talking about the probability distribution and assumptions we make. So in order to make some inference about the process, we need to make assumptions. Okay. Suppose in this case, if you're tossing a coin, we have tosses of 100 coins. Let's just make it like 100, we believe that the coin is only two-sided. Okay, so if the coin is two-sided, because that's the assumption we make, then the process which generates this data could follow a binomial distribution. So what binomial distribution means is that it can possibly have two outcomes. And we are trying to believe that the process which generated this is a binomial distribution which kind of generates this data. Suppose if you are trying to find out, you have data of flight arrival time, okay, like arrival time of flights in an airport, and the data is collected, okay, and if you wanted to find out the process which could have generated it and try to estimate what will be the next arrival time of the flight, then that assumption we make is that it could be a Poisson distribution because we are trying to find out data, interval data. Okay. Suppose if we are trying to find out the height of students in a university or height of citizens in a particular state, then we assume that the data comes from a normal distribution because the height could vary from, let's say, 150 centimeter to 170, 80 centimeters. So that could be the variation. And whatever data we observe, we believe that it comes from normal distribution because without making assumptions, we cannot try to infer. We cannot try to move on to the next step. So here in this case, we assume that the data, generated is heads and tails. So it could be from the normal distribution. So what is the formula for normal distribution? Like this is the formula for normal distribution. Okay, the n is the number of trials. C is the combination, permutation and combinations, right? In CP, that's the combinations, and R is the number of events for which we have seen success. The outcome is what we observe. Okay, and P is the probability of success. Q is the probability of failure. Okay, so let's assume that because we made an assumption that it comes from normal distribution, we made 100 tosses, coin tosses. So N is 100 and C. R is, let's say, 55 times my coin toss has resulted in heads. Okay, that's the observation I have. Okay, I have tossed 100 times and 55 times my coin has resulted in heads. So that is R, 55. 55 is the number of times my coin has resulted in heads, and 45 times the coin has resulted in tails. That's what it means. Okay. We are not trying to find whether the coin is fair, we are trying to estimate the probability of P. Now, we wanted to find P hat. Okay, anything which you estimate, we call it as P hat. Okay, so just another terminologies, anything which is from the population, we call it as mu, and anything which is from sample, we call it as S. Okay, for mean, the standard deviation will be sigma for a population, and standard deviation will be yes. Okay. Okay. Let's carry on. Means P is the probability of success. Probability of success is what we wanted to find, the probability of success, and R is the number of times we got heads, and we can write Q as 1 minus P, because probability of success plus probability of failure is equal to 1. All probabilities should P plus Q should be equal to 1. Any probability should have a total of 1. So we can write Q as 1 minus P, because it is the inverse of this, right? So we can write P as 1 minus P, and N minus R. N is 100, R is 55, so this becomes 45. So this is your binomial distributions function, and we have plugged in the values of our experiment. 55 tosses, 100 tosses. Out of this 55 we got heads, and 45 times we got tails. Okay, and now in order to find out what is the probability, and if you wanted to maximize the probability of P, we can use derivatives. If you remember, in derivatives I talked about maximization and minimization. If there is a function, and if you wanted to find out the maximum of a function, the slope at the maximum point will be 0. Okay, if you want a minimum of a function, the slope at the minimum point would be 0, which means that we are trying to find out the point in this curve where the slope becomes 0 and it is maximum, and here it is minimum. Since it's a maximization problem, which means that we want to maximize the probability of observing this data. So if you look at the definition of any statistical terms, it will be confusing. I don't know who writes it. Even for a native English speaker, I don't think they will. It is that easy to understand what those definitions and mean. Okay, if you read about what MLE, it will talk something like the probability of observing the data, maximizing the probability of the data which has been observed, or something, which I don't know if it makes sense, but anyway, I'll try to explain what it is. So we're trying to maximize the probability of observing whatever we receive as an observation. Let's say 55 heads and 45 tails. Okay. So now, in order to make our computations easier, we can use logs. Okay, because this is all multiplications. If you use log, multiplication becomes additions. One of the property of log is so we'll use natural log, and we'll try to convert these multiplications into additions. Okay, so here it becomes log of natural log of 100C55 plus, okay, if you take log, it becomes log of P55 plus log of, okay, the multiplication becomes additions, and it becomes like this. Okay, and log, the property of logs, this is a constant, so no change. You can log 2 to the power of x is x log 2, right? So you can write it that way. So it becomes 55 log p. This becomes 45 log 1 minus p. Now, if you wanted to find the maximum of anything, we can set the derivative. We can find the derivative of this function, okay, with respect to p, which means that we are trying to find the change, a small change in probabilities, and we are trying to find the impact of it and trying to find the maximum of it. So that's what we call this maximum likelihood estimate. Maximum likelihood estimates. Likelihood is to find out what is the probability of finding this data which we saw, which we noticed, okay, and trying to find the likelihood of it. So this is what it is. If we set this to 0, we can set the derivative. Okay. Now derivative of this is constant is 0, because it does not have anything which changes with p. This will be 0, and this becomes (55) log of natural log of p. Okay, if we take derivative, it becomes 1 by p. It becomes 55 by p, okay, plus 45, and becomes again natural log of x becomes 1 by x, it becomes 1 minus p. And if you see there is a using chain rule, we have to take derivative of the function inside 1 minus p, it becomes this becomes minus 1. So if this is minus 1, then it becomes 55 minus 45 into p into 1 minus p is equal to 0. Okay, this is the equation. Okay, now if you see, if you try to solve for this, it becomes 55 into 1 minus p minus 45p divided by 1 minus p equal to 0. Okay, let me erase this. Okay, now we are here, just two steps. 55, okay, this becomes 55 minus p minus 55 minus 55p, sorry, 55p minus 45p equal to 0, because this goes the other side, becomes 0. Now 55 minus this becomes 100, 100p is equal to 0. So 100p is equal to 55. So p is equal to 55 by 100 and p is equal to 0.55. That is the estimated. Okay, so this means that for our coin tosses which we had, hope you are able to see it. Okay, for our coin tosses which we had 55 heads and 45 tails, the probability of getting heads is equal to 0.55. So we do not assume that it is 0.5 all the time. If you wanted to estimate from the data, this is what the data says. Okay, we are taking the probability of heads is 0.5. Okay, 0.55. So this is how you calculate and estimate probabilities from data. This is what you call it as maximum likelihood. Okay, and this is a very important process in trying to estimate probabilities. Let's assume that you have a different problem. Let's say you have data like before that I'll just do a recap of this to make sure that we understand this. So we are trying to estimate the probabilities of data which we observe. We observe 55 heads and 45 tails, and we are trying to find out, the probability of heads based upon the data, and we kind of assume that it is a binomial distribution because coin can have only two outcomes, head or tails. And when you put it into this this formula, we don't know what P is. We don't know what Q is, and we're trying to find, with the rest of the information, we're trying to find P. That's why we call it as estimation. So ML is maximum likelihood estimation, so P hat. Okay, and we're trying to set the derivative. We take logs to make our calculation simple, because if you take logs, the multiplication becomes additions, and so this becomes 3 different additions. And if you use the property of logs, you kind of use the quotient goes, the power goes to the quotient, and this is how you can rewrite it. And when you set the derivative to 0 to find the point where the function is maximum, you can set it to 0 and find the value of P. Okay, the P is 0.55, 0.55. Okay, that's the value of P. Now this is the statistical way of learning. Okay, but when it comes to machine learning and data science, we can learn this MLE using the gradient descent, which we discussed. Okay, as I mentioned, gradient descent is a way to kind of randomly initialize and start the maximization problems from somewhere. Okay, maybe you can use gradient ascent because we are trying to find the maximum, right? We can use gradient ascent and try to go in the direction of the slope where it is maximum, and when it starts dropping, maybe this is the point. Okay, so in practical scenarios, we cannot set large complex functions and set it to 0 and find the derivatives like this. We did it in the toy example. So we use gradient ascent to find the maximum of a function using using the partial derivatives and stuff like that. And if there are more variables involved, we use partial derivatives and things like that to get it done. Okay, that's how we are connecting the dots between statistics and how it is practically implemented in algorithms in machine learning. Okay, we use universal approximator like neural networks to kind of learn this function. Okay, we don't know that this is a binomial distribution, so we assume the neural network to learn the arbitrary functions, and it could learn a binomial distribution function as well. Okay, and it would use gradient ascent to find the maximum. Okay, that's how practically things are solved. Okay, all right. So I'll give one more example of MLE. Okay, let's go. Okay. If you try to want to find the maximum likelihood of these numbers, okay, which means that I have three numbers. I know only this. I wanted to find the maximum likelihood of a number from this. So if you look at this data, okay, it looks like it comes from a normal distribution. Okay, the assumption we make. Again, we have to make assumptions. Okay, I'm just giving it our example because it's easy for us to relate. And the normal distribution could be like this. The values are 4, 5, 6, a standard deviation of 1. That is one standard deviation from the mean. Okay, this is what is the data distribution. So what we can do is, if we want to estimate the probability of this kind of data, we can even use instead of binomial distribution, we can use the equation for the function for normal distribution, x minus mu by sigma square. Okay. This is the equation of the normal distribution. So the process is the same. We can assume that the data is independently arrived. Okay, we have three numbers. Let's say it's it could be anything actually. If you have like any random numbers like this, which is forming a distribution, you can assume that it's a normal distribution. And if you assume that it is independently arriving, then we can get the probability density functions of like probability of the value of x is equal to 4 into probability of x is equal to 5 into the probability of x is equal to 6 by just multiplying the probability distribution functions, like plugging in the value of x is equal to 4, 5, 6. Okay, and you have three equations here, 4, 5, 6, one for each. Okay, and if you try to do the same process which I explained, okay, try to derive, take the derivatives and set it to 0 and try to find the value of, we can find the value for x, partial derivative with respect to x and partial derivative with respect to u. You will be able to find the x and mu. Okay, if you try exactly the same example, and you will end up getting the value of x is equal to sum of 4 plus 5 plus 6 by 3. Okay, 15 by 3, x is equal to 5. This is the 5, probably the standard deviation, probably you will get it as 1. Okay, this is, if you try to this in exercise, probably you will find it. Yeah, a little bit complex because it involves E and things like that, but it's doable. Just a hint, okay, log e to the power of x is, derivative of e to the power of x is itself. So you will get this as a derivative. And if you use, if you just rearrange these terms to, like sigma squared, if you take it to the numerator, you can use the logs to kind of bring the quotient, exponent to the quotient and trying to use and solve this problem. Same problem. Okay, very simple. And nothing. You can visually find out that this exactly matches with what we would do normally. We wanted to find the mean. Okay, like 4 plus 5 plus 6 by 3. If you wanted to find out, if you want to find out, guess what is the probability distribution of this any three numbers. Mean is always a good estimate, right? So if you that's the safest estimate. So if you say that okay, it comes from the distribution of the mean 5, that's what this says actually. Okay, this is 9 plus 6 plus 3, mean is 5. The standard deviation of 1. So if you wanted to generate more data with mean, so you can even generate data like randomly. If you choose, if you allow the computer to kind of randomly generate data with mean, mu and sigma. This is sigma. With mean, mu and standard deviation as 1, it'll generate data for you. Okay, and it could generate data like 7 or 3 or 9. So, but it will all form this pattern of normal distribution. Okay, that's what this really means. If you are able to with this mu, okay, this is actually mu, this is sigma. Okay, we are trying to find this mu and sigma, right? Okay, this x is the input values 4, 5, and 6. Okay, so this is another example of maximum likelihood estimate using normal distribution, and this can also be solved in machine learning or deep learning using neural networks, and we try to use gradient descent to find the maximum. Okay, yeah, one small correction regarding the sample mean. I just said that it is yes, it's actually x bar if it is sample mean. Okay, and standard deviation for population is yes, actually. So this is for population, this is for sample. This just to correct it actually. Mu is for population, sigma is for population, x bar is for sample, and s is for sample. Okay, mean and standard deviation. Thank you.